Howdy, howdy, this is Mr. Potter. In our last video, we talked about different types of transformations. We talked about translations, moving a graph side to side or up and down. And we also talked about reflections, where we can reflect a graph over the x-axis or the y-axis. What we're going to be talking about today is we're going to be talking about our third type of transformation, the one that we're going to be using, which is a little bit more complicated, and that's dilations. And we're also going to talk about how we can put these transformations together to basically put a graph wherever we want it or wherever we need it. So we're going to start talking about what a dilation is. So a dilation is a stretch or shrink in the horizontal or vertical direction. In other words, if I was to have some type of graph like my parabola, my y equals x squared graph, let's try and graph that correctly. So if I have some type of parabola like this, I could stretch it vertically. In other words, make it so instead of going through the point 1, 1, I'm going through the point, say, 1, 3. And of course, that means that this point 2, 4 that I was going through would have to be vertically stretched 3 times as far. So it's actually going to be going up to the point 2, 12. And so if I have, starting at the origin, going up to 1, 3, and then 4, 5, 6, 7, 8, 9, 10, 11, 12 up here. So I would have a graph that's basically 3 times as tall going through each of these points. And of course, because of symmetry, I would be having the same thing over here. So I can stretch it vertically, or I can compress it, make it a little bit shorter, make it only half as tall. In other words, going through the point 1, 1/2, or the point 2, 2. Of course, still going through the origin, it's going to make my parabola a little bit shorter. So what we're talking about with these dilations is we're talking about either stretching or shrinking. And this stretch or shrink can happen in the horizontal or vertical direction. We're going to be talking about the vertical direction first. So for our purposes, we're going to basically say that g of x is going to be equal to a times f of x. In other words, whatever my original function is, by putting a coefficient in front of it, this coefficient is going to determine how much of a stretch we're dealing with. Now you may recall from our last video that if this is a -1, that's actually going to reflect it across the x-axis. What I'm emphasizing in today's video, though, is the magnitude of a. So in other words, if the absolute value of a is greater than 1, then we're talking about a vertical stretch. And if the absolute value of a is less than 1, then we're talking about a vertical shrink. So I want to do a couple of examples here. My first example is I want to take the parent cubic function by a factor of 3. And because I'm doing my parent cubic function by a factor of 3, then this a value that I'm referring to is my 3. And my function is going to look like y equals 3x cubed. Notice I'm taking my parent cubic function. This is my f of x. And I'm just putting that coefficient in front of it. Now, what this does, because I'm stretching by a factor of 3, I'm actually stretching it. This is our vertical stretch. So normally our function is going to pass through the origin and the point 1, 1, and the point 2, 8. Again, counting by 2's here just to make this a little bit more to scale. And of course, this is an odd function, so I'm going to have that symmetry as well. But what I'm doing is, because I'm stretching it by a factor of 3, instead of going through the point 1, 1, I'm actually going through the point 1, 3. And instead of going through the point 2, 8, I'm actually going through the point 2, 24. So 10, 12, 14, 16, 18, 20, 22, 24, all the way up here. And so my graph ends up being stretched, of course, assuming that I can actually draw correct numbers. Similarly, this is 1, 2, 3, and down to negative 24. So we're going to be looking at another graph that's going to go like this. Notice that this pink graph is a vertically stretched version of this white graph. So let's do another example of this. Let's do our parent reciprocal function. By a factor of 1/2. So, of course, because I'm doing by a factor of 1/2, notice because a is less than 1, this is going to be one of our shrinking. And for us, a is 1/2. So our function is going to be y equals 1/2 times 1 over x, or really 1 over 2x. And so what happens when I look at my original function, remember my original function, when x is 1, y is 1. When x is 2, y is going to be 1/2. When x is 1/2, y is going to be 2. So I actually have a graph that looks kind of like this. For our purposes, when x is 1, the reciprocal of 1 times 1/2 would only go half as far above the x-axis. This one's going to be 1/4. This is going to be 1. And so what happens is I still have this asymptote though. So my graph ends up being vertically compressed. And similarly, it's going to be vertically compressed over what this part of our graph would look like. So notice that basically all the points in yellow are half as close to this x-axis. Whereas over here, all of the pink points are 3 times as far away from our x-axis. So that's what's happening in a vertical dilation. So the next thing I want to talk about is what is a horizontal dilation. And so it's going to be very similar for us. For a horizontal dilation, by a factor of b, what we have is g of x is equal to f of b times x. In other words, just like before, when we're dealing with stuff that happens in our horizontal aspect, the coefficients, the mathematics, the algebra actually takes place within these parentheses of our argument. And what's also similar here is that if the absolute value of b is greater than 1, then this is a shrink. And if the absolute value of b is less than 1, this is a stretch. And of course, notice that both of these, very similar to what we were talking about for translations, are counterintuitive. Because we expect if b gets bigger, we're talking about a stretch, but we're talking about on the x-axis. So what's actually happening here is that instead of going through the point 2, 2, we're basically doubling x and it's going through the point 4, 2. In other words, because it's going out twice as far, whatever my graph happens to look like ends up being stretched out. But I want to know what value makes this 2, so I'm going to have 1/2 of 4 to make this a 2. That's why a value that's 1/2 ends up being stretched out, and a value that's greater than 1 ends up being shrinked. And I think this will be a little bit more clear when I go through some examples here. So what I want to do here is I want to dilate our parent square root function by a factor of 2. Now, of course, remember that we're talking about where our g of x is equal to f of b times x. For us, b is this value that we're talking about. b is 2. So our function is going to be y equals the square root of 2x. Now, I'm used to what my parent function looks like. Normally, my parent function is only in the first quadrant. Goes through the point 0, 0, goes through the point 1, 1, goes through the point 4, 2. So in other words, if I was looking at this from a table, this is what my table would look like. Well, actually, this is not y, this is just the square root of x. What I want to know is, what does the square root of 2x look like? Well, 2 times 0 is 0. Square root of 0 is 0. 2 times 1 is 2, and this ends actually being the square root of 2. 2 times 4 is 8. This ends up being the square root of 8, which is about 2.828. This is about 1.414. So what's happening is that when I go over 1, I'm actually going up 1.414. So I'm actually ending up here. Similarly, when I go over 4, I'm actually up 2.828. I'm actually up over here. And so my graph actually ends up looking like this graph has been moved over. This point's kind of been moved over here. This point's kind of been moved over here. This looks like the point 2, because 2 times 2 would be 4, and the square root of 4 would be 2. Looks like this point would correspond to this point here. So what happens is my graph ends up looking like it's being compressed by a factor of 1/2. These pink points look like they're being compressed. If I do another example of this, if I take a look at our parent absolute value function, by a factor of 1/4. Now for us, b is 1/4, and this ends up being a stretch. So if I take a look at my absolute value function, again, what I expect from my normal absolute value function is, of course, it only takes place in quadrants 1 and 2. I got the point 0, 0, the point 1, 1, the point 2, 2, the point 3, 3, all of these points along this line, and all of their counterpoints in quadrant 4. For our purposes, though, if I were to take a look at this table of x's and absolute value of x's, 0, 1, 2, gives me 0, 1, and 2. But if I take a look at the absolute value of a fourth x, a fourth of 0 is 0, which gives us this point. And we notice that the origin really doesn't change. The absolute value of a fourth x is a fourth, so that ends up being over 1 up a fourth. The value of the absolute value of 1/4 of 2 is 1/2. And so this means it goes over 2 and up a half. And so it actually ends up looking something like this. Similarly, this is going to go through this point over here. And so it looks like this white graph is being stretched out, even though our value of b is 1/4. So again, it is counterintuitive when we're talking about horizontal stuff happening. So it's just something to be aware of, that we're going to have to make sure that we stretch whenever our b is smaller than 1, that we shrink whenever our value of b is more than 1. One of the things that we should note is that our horizontal dilations are always from x equals 0. In other words, they're always from the y-axis. Similarly, vertical dilations are always going to come from y equals 0. In other words, they're always going to come from the x-axis. And there's also something else that we need to note, is that the order matters. So I want to do an example of where the order matters here. So let's talk about a comparison of two functions. I'm going to do this function twice. In both of these, we're going to be dealing with y equals x squared. And in both of these, we're going to translate right 3 units. And we're going to dilate by 1/2. So my question is, what happens when I translate first versus when I dilate first? So normally what happens is that when I'm talking about a parabola, I know the parabola has to go through the point 0, 0, then through the point 1, 1, and through the point 2, 4. So if I translate first, here is my original parabola. The first thing that I'm going to do is move everything to the right 3 units. which means now, instead of being at 0, 0, I'm now at the point 0, 3. This point's been translated 3 units. This 1, 1 translates to the point, excuse me, not 3, 0, 3, 3, 0. This 1, 1 translates to the point 4, 1. And this 2, 4 translates to the point 5, 4. And similarly, these negative points are translated 3 units over as well. So this yellow parabola represents a translation of this pink parabola. But my actual answer also has to include this dilate by 1/2, which means all of these points end up having to be twice as far from the y-axis, twice as far from x equals 0, which means this point, which was at 3, 0, is now at the point 6, 0. This point, which was at 4, 1, now has to be at 8, 1. And this point, which is at 5, 4, now has to be at 10, 4. So in other words, my parabola ends up not only widening out, but it also ends up being shifted over really out here to 6. So it's something to be important that when I'm translating first, I end up with this graph. What happens if I dilate first? Well, of course, starting off with our original parabola, 0, 0, 1, 1, and 2, 4. If the first thing I do is dilate, if I do dilation first, then these are all going to be twice as far away from my axis. Well, twice 0 is 0. So I'm still at the origin. Twice 1 is 2, so now this is at the point 2, 1. And twice 2 is 4, so now I'm at the point 4, 4. And so this parabola ends up widening first before I actually go about translating it. For reference, here's my original parabola. Then what I need to do now is I need to translate each of these yellow points over 3 units. Well, 0, 0 becomes 3, 0. 2, 1 actually becomes 5, 1. And 4, 4 becomes 7, 4. So in other words, all of these points get translated over 3 units, but it's not the same points that we were talking about in our previous example. And so what we notice here is that the order is important. So because order is important, we need to kind of standardize ourselves an idea here. So in general, what we're going to see is we're going to see g of x being written as f of b times x minus h. In other words, I'm always going to see this stretch coefficient or the shrink coefficient, this dilation coefficient being factored out inside of the parentheses. So what we're really after is we're really after this type of situation. Order of operations says that we need to do multiplication before we do addition. So I need to do something like this. So in general, when we're talking about doing these combinations of transformations, in general, we're talking about g of x is going to be a times f of b times the expression x minus h inside the parentheses plus k. So we're going to be doing it in the following order. We're going to take care of parentheses first, so we have to do the horizontal stuff first. And we want to dilate horizontally before we translate horizontally. And similarly, because we do multiplication before we do addition, when we do 3 and 4, when we do our vertical stuff, we want to dilate vertically before we translate vertically. So we really want to do things in this order. It's going to make the most sense for us to do it this order. One, because it's consistent with our order of operations that we've learned about before. But number two, it's going to get us a consistent result. So I want to finish up by doing an example of this. So let's take a look at this problem. I'm going to have y equals 1/3 of 4x minus 8 squared plus 4. So what we're looking at here, we know that f of x, the parent function that we're considering, is x squared. We know that we are translating vertically 4 units. We know that our dilation factor vertically is 1/3. And if we factor out this 4, that's really what's being squared. So for us, b is 4, and our translation is going to be 2 units. So I want to take a look at everything that's happening here. First off, I'm dealing with a parabola. And of course, I've got the point 0, 0, I've got the point 1, 1, and I've got the point 2, 4. So this is my raw parent function. This is what I'm dealing with. And we said that we have to take care of this horizontal dilation first. So the first thing I need to do is multiply by a factor of 4. Well, keep in mind that a factor of 4, this is a shrink. So in other words, what's going to happen is now, if I multiply 0, 0 by a factor of 4, that's going to give me 0, 0. If I shrink by a factor of 4, that means x is only going to be 1/4, 1. And if I shrink by a factor of 4, this is going to be 1/2, 4. So in other words, my parabola is very narrow. Should be 4 times as narrow as this white parabola over here. And that's going to be my first step. My first step is to shrink. The second thing that I'm going to do is I'm going to translate. And notice, because I've got a minus here, I'm actually translating to the right by 2 units. So 0, 0 is going to get translated. So let me draw that down here. 2 units to the right. So instead of being at 0, 0, we're actually at the point 2, 0. Instead of being at 1/4, comma 1, we're actually going to be at 9/4, 1. And instead of being at 1/2, 4, we're going to be translated over 2 units. So we're actually going to be at the point 5/4, 4. And if you're not comfortable with these fractions, you really need to get comfortable with fractions. It's time to let them be your friend. Of course, it's also nice if you can draw, which I can't, but we'll deal with this. So it should be 5/2. I'm sorry, 5/2. Let's try that. I gotta let them be my friend too. So once I've done that, now what I need to do is I need to take care of this stretch. In other words, these values are going to stretch up. Actually, excuse me, if it's a 1/3, shouldn't it shrink? This is going to be a shrink as well. In other words, things are going to get smaller by a factor of 1/3. So now, each of these points are going to get shorter by a factor of 1/3. So this 2, 0 is still 2, 0 because 1/3 of 0 is 0. 1/3 of 1 is 1/3. So now this is going to go over 9/4 and only up 1/3. So this is 9/4, 1/3. And then 1/3 of 4 is 4/3. So it's going to be 5/2, 4/3. And this is the point where I start saying, okay, this parabola is starting to widen up again. And it's something that's convenient to notice is that a shrink in one of these directions actually looks like a stretch in the opposite direction. But it's not always the same magnitude. It's not always the same distance. It's not always the same scale. But it is helpful to think of a shrink in the horizontal aspect really being a stretch in the vertical aspect. And similarly, a shrink in the vertical aspect would look like a stretch in the horizontal aspect. The final thing that we have to do that's going to give us our final answer is that we're going to move our graph up 4 units. So I'm going to have basically stuff that looks only like it's in the first quadrant. This point 2 is being moved up 4 units, so it's over 2, up 4, and that's going to be here. This point's going to be 9/4, so it's going to be just slightly over, and it's going to be up 4 1/3. So 9/4 and 13/3. And then this point's going to be moved up by 4 units as well. So 4 plus 4/3 is going to be 5 1/3 or 16/3. So it's going to be 5/2 and 16/3. And here is our parabola. Now, of course, keep in mind that because we are sketching, it's not going to be very accurate, which is why I'm labeling these points. Understanding these points, these values, are really helping us to internalize what's happening here. I see that my graph has moved over and up, but these points tell me how much it's moved over and up. I know that my graph has basically compressed horizontally and has compressed vertically as well, but these coordinates tell me how much it's done so. They're very important. And so you need to make sure that when you're graphing, when you're sketching these graphs, you try and be as accurate as possible, but you need to be precise as possible with the coordinates. Once again, this is Mr. Potter. Thank you for watching. Have a great day.